In this video, we are going to learn about the ideal and non-ideal solutions. In the previous videos, while discussing the gas laws, we have seen the ideal gas. Now we are going to see what is ideal solution. An ideal solution is a solution in which solute-solute and solvent-solvent interactions are almost similar to that of solvent-solute interaction. It means that in the solution we have solute-solvent type of interactions, and those interactions should be similar to that of solute-solute and solvent-solvent in order to call the solution as an ideal solution. In order to understand this, let us see the diagrams. Here the first beaker contains solvent, and in solvent the interaction is AA, and the second box contains solute. In this we have BB type of interaction. And you know that if we mix the solute with solvent, we are going to get solution, and the solution will have three types of interactions, that is solute-solvent and solvent-solvent and solute-solute. In the solution, if the interaction between the solute and solvent is similar to that of solute-solute and solvent-solvent, then this type of solution is considered as ideal solution. Now let us see the conditions which are necessary for calling a solution as an ideal solution. The first condition is the solution must obey the Roults law. The second condition is delta H of mixture should be equal to 0, that is enthalpy change of the solution should be equal to 0. That means no energy should be evolved or absorbed while forming the solution. The third condition is delta V of the mixture should be equal to 0. That means change in the volume should be equal to 0. This can be expressed as there should be no expansion or contraction on mixing the solute and solvent to form solution. Here on the board we have given 4 examples which are almost similar to ideal solution. First one is the mixture of benzene and toluene. The second one is the mixture of N-hexane and N-heptane. The third one is the mixture of ethyl iodide and ethyl bromide, and the last one is chlorobenzene and bromobenzene. These are the 4 examples which are almost similar to that of the ideal solution. If we draw the graph of the ideal solution, we are going to get a graph like this. Here the mole fraction of the solvent is 1, solute is 0. When it comes to this point, mole fraction of a solvent is 0, solute is 1. And this line shows the partial vapor pressure of the solvent. This line shows the partial vapor pressure of the solute. This line which is on the top shows the total pressure, that is equal to PA plus PB. Now let us see the definition of a non-ideal solution. Non-ideal solution is a solution which show deviation from Roults law. Remember that the solutions which obey Roults law are known as ideal solution, whereas the solutions which deviate from the Roults law are considered as non-ideal solution. And when it comes to the delta H and delta V values, delta H value, that is change in enthalpy of a non-ideal solution, is always greater than or less than 0, but it is not equal to 0. And when it comes to the change in volume, it is also greater than or less than 0, but it is not equal to 0. Remember, when delta H and delta V values are equal to 0, then it is ideal solution. When it is not equal to 0, that is greater than 0 or less than 0, then those solutions are considered as non-ideal solutions. Non-ideal solutions show 2 types of deviation. The first one is positive deviation and the second one is negative deviation. Here we have given the examples for the positive deviation and negative deviation. The examples for the non-ideal solutions exhibiting positive deviations are the solution of ethanol and water, the solution of CS2 and acetone, the solution of carbon tetrachloride and benzene, the solution of ethanol and cyclohexane, the solution of CCl4 and toluene, and lastly the solution of CCl4 and CSCl3. that is carbon tetrachloride and chloroform. And when it comes to the examples of non-ideal solutions exhibiting negative deviation, we have chloroform mixed with acetone. The second example is water mixed with HCl. The third example is water mixed with nitric acid. The fourth example is chloroform in benzene. And the fifth example is methanol in acetic acid. These are all the examples for the non-ideal solutions exhibiting positive and negative deviations. Remember, when it comes to the positive deviation, the graph will be in this way, and when it comes to the negative deviation, the graph will be in this way, which we are going to explain now. As we have seen in the non-ideal solution, a non-ideal solution shows positive deviation and negative deviation. Let us see the positive deviation. In positive deviation, AB interactions are weaker than AA and BB interactions, and the observed vapor pressure of each component and the total vapor pressure are greater than the predicted by Roults law. In non-ideal solution showing positive deviation, the interaction between the solute and solvent is always weaker than solute-solute and solvent-solvent interactions. And one more thing, the vapor pressure of the each component and the total pressure of the solution will be greater than the predicted value by Roults law. Here you can see that the vapor pressure of A component is greater than the predicted value by Roults law, and vapor pressure of a B component is greater than the predicted value by Roults law, that is PB naught into XA. And when it comes to the total pressure is greater than the sum of the vapor pressure of A component and B component. And always remember that for non-ideal solutions showing positive deviation, the delta H, that is change in enthalpy of the mixture, will be greater than 0, and delta V naught, that is change in volume value, will also be greater than 0. And when it comes to the graph, for positive deviation, this is total vapor pressure value, this is partial vapor pressure value of the solute, this is partial vapor pressure value of the solvent, and you can see that these all three values are greater than the ideal solution values. Now let us see the negative deviation of a non-ideal solution. When it comes to the negative deviation of non-ideal solution, remember that AB interaction are stronger than AA and BB type of interactions, and the observed vapor pressure of each component and the total vapor pressure are lesser than the predicted by Roults law. Remember that here in non-ideal solution exhibiting negative deviation, the interaction between the solute and solvent is stronger than the solute-solute and solvent-solvent interactions. Remember, here the vapor pressure of each component and the total vapor pressure is always lesser than the predicted value by Roults law. Here also you can see that PA is lesser than PA naught into XA. PA naught into XA is nothing but the predicted value by Roults law, and PA is the calculated value for vapor pressure. For non-ideal solutions showing negative deviation, PA is less than PA naught into XA and PB is less than PB naught into XB. This is the predicted value by Roults law, and PB is the calculated value. When it comes to the total pressure is less than the sum of the vapor pressure of both the components. Remember, for the non-ideal solution exhibiting negative deviation, delta H value and delta V value will be less than 0, that is change in enthalpy and change in volume will be less than 0. When it comes to the graph of non-ideal solutions exhibiting negative deviation, we are going to get the graph like this, in which the values are lesser than the ideal values. If you see here, this is the positive deviation and this is negative deviation. For negative deviation, the lines in the graph are below the values of ideal solution. This is the total pressure of a non-ideal solution exhibiting negative deviation which is less than the sum of the vapor pressure of both the components. So this is the description of a ideal solution and non-ideal solution, and we are going to see the colligative properties in the next coming video.